Hello everyone. I welcome you all to my talk on almost correct invariants, synthesizing inductive invariants by fuzzing proofs. This is a joint work done by me, Sumit Lahiri, and my research guide, Shubhajit Roy. I am a third year PhD student presenting this work for ISTA 2022. Without much further ado, let me get started with the main slides. Program verification is the task of proving programs correct upon executing with all inputs. And one popular way of doing so is with the use of hot triples. They typically look of this following form, where P, Q, R are the three components. P and R are conditions that are expressed in some base logic. That's why they are in curly braces. Formally, the way a hot triple works is that if we start from a state S1 that satisfies the conditions in P, known as the preconditions, then upon executing Q with S1, if it halts, it must halt in a state S2 that satisfies the conditions in R, known as the postcondition. We use the following notation all throughout the slides and also in the paper in order to specify the hot triple, that is the specification along with the program P. Hot triples makes it easy to do program verification. However, programs with loops requires guessing an inductive loop invariant in order to establish its correctness proof. There are existing tools that require logical encoding of the program to synthesize an inductive invariant, an example of which is CodeTwin here. I show a schematic of this tool. It takes in the program source, converts it into a logical encoding, and then the tool proposes a invariant. Both the logical encoding and the invariant are dispatched to a theorem prover. If the invariant is valid, then the theorem prover comes with the correct verdict. But in case if the invariant is invalid, then the incorrect verdict is produced and the counter example from the theorem prover is passed on to the tool in order to propose a better invariant in the next round. However, we ask the question, what to do in case of programs that contain opaque operations? We consider opaque operations to be those whose formal semantics are not available, such as external function calls, vector instructions, system calls, floating point instructions, etc. Here, I show a program on to the left. This is the multiplication program, which iteratively does multiplication and finally produces the result of A0 into B0 in R. On line number 7, we have a call to built-in citizen. On architectures where built-in citizen is supported, shown by the supported flag, this iteration converges very, very quickly. However, it is an opaque operation. It is a compiler primitive to make this function faster, but the semantics of this is not known. Logical encoding of this kind of program is not possible, so the existing tools fail. However, our tool is automatically able to generate the following invariant for this program on the left, which is this invariant here. Formally, I come to the problem statement. Given a specification 5P P 5 post, where the program P may contain some kind of opaque operations, we attempt to synthesize an inductive loop invariant I that establishes the correctness proof. The main contribution of our work here is as follows. We can work with programs that contain opaque operations, and it is quite comparable to the state-of-the-art tool. We devise a technique known as proof fuzzing in order to verify the correctness of the inductive loop invariant I. Along with that, we implement our ideas into a tool named Achar. Well, in Sanskrit, Achar means immovable or invariant, and thus the name. Over here, I show a schematic of how the tool works. The tool starts by taking the source code of the example program, passes it on to the tool's front end. Then the learner proposes an invariant I and passes it on to the teacher component, which is the counter example generator. The teacher component combines two things together. First is the specification along with the invariant I into a non-deterministic program p hat of I. This is used for proof fuzzing. Here I go into a little bit detail of what p hat of I actually looks like. Well, on to the left, I show the specification. This is a program containing a while loop along with 5 pre and 5 post and the invariant I. Both of these are combined together by the p hat of I transformer into this p hat of I program. The crux of proof fuzzing is as follows. If we hit any of the lines on L1, L2, or L3, which is line number 6, 15, or 19, then in that case, the invariant is deemed invalid for the given program and specification. However, if none of the three lines are ever hit and the program exits by returning from line number 20, then in that case, the invariant I is valid for the given specification. What we do in practice is that we take this p hat of I program and fuzz it with multiple inputs in order to check on which of the lines it actually returns. Now I come to the theorem which shows the correctness of proof fuzzing. If any of the execution of p hat of s, where s is the initial program state on which p hat is invoked, if it reaches any of the goal points L1, L2, or L3, that is p hat is returning top in this case, then in that case the invariant I is not valid and s can be taken as a counterexample or a witness to the fact that the corresponding assertion failed. However, upon fuzzing or for any of the s that we try out with, if p hat of s does not hit any of the lines L1, L2, L3, rather it exits from the last return, that is p hat can only return bot, then in that case the candidate invariant I can be taken as a valid witness to the correctness of the specification that we have. What happens here after this step is that p hat of I is dispatched to the reach oracle abstraction. For us, this reach oracle is what we implement with the help of fuzzers and other tools. Here in the clouds, I show the tools with which the reach oracle was made. Our primary implementation of reach oracle is using the Hongfuzz backend. Upon giving p hat of I, if reach oracle produces top as the verdict, then the counter example so produced from reach oracle is passed on to the learner, and the learner tries to propose a better invariant in the next round. However, if reach oracle produces no counter example and it directly produces bot, then in that case the invariant I is deemed valid, and in green I show it in success saying that the inductive invariant I holds. We did the following experiments in order to better understand Achar and to compare it with the state-of-the-art tools. The first question that we ask in our Q1 is that is Achar effective at synthesizing invariants? What is the runtime cost of Achar? How well Achar performs using a hybrid strategy? And what are the hyperparameters and heuristics of Achar useful? How useful are they? In interest of time, I will not be discussing the results of RQ3 and RQ4. However, I'll go into brief details of how RQ1 and RQ2 were evaluated. I urge the viewers to read through our main paper for more details on the hybrid strategy and the hyperparameters we use to tweak Achar. Synthesis effectiveness and runtime cost. Here I show two plots. These are cumulative cactus plots. Here in red, I show the performance of the state-of-the-art tool, Code to Win, and in green, we have our own tool, Achar. The 10-second here denotes the time reach oracle was given in order to find any counter example for the given invariant. Here I show the plot of time taken versus instances solved and the number of counterexamples versus instances solved. As you can see, the two graphs are quite compatible. However, do note that Achar runs a bit slower because of the Hongfuzz backend or because of fuzzing. In summary, we carried out our experiments in 133 benchmark examples, of which Achar was correctly able to solve 100 and Code2Inv solved 92 benchmark examples. Apart from the 100 correctly solved examples, Achar was wrong on 5 examples. We increased the timeout with which Reach Oracle was run to 4 hours, and doing so, we could invalidate 4 of the 5 wrong results. However, using a still stronger backend or a better implementation of Reach Oracle with Hongfuzz and Colossus, we could invalidate all 5 results, and we additionally solved 2 more examples. But the issue is that Colossus ran with a much higher runtime cost, and that is why it is not the default implementation of Reach Oracle. Colossus is a tool that comes from our lab itself. It is by a former PhD student. Here I refer to the tools paper, Deferred Concretization in Symbolic Execution via Fuzzing. Here I show a benchmark suite of 15 programs. We call this the Open Programs benchmark suite. We made these examples in order to show the effectiveness of Achar over programs that contain opaque operations. Here I show the type of opaque operations along with the description and the time Achar took in order to find the invariant and the number of counter examples it required. In interest of time, I would be discussing in details about example number 13, which invokes a convolutional neural network. However, in the paper, we do explain the multiply example and some parts of the sum of squares example. I urge the viewers to have a look at the same. Here I show the overview of how example number 13 works. We start with a matrix of 100 elements. Each column contains numbers from 0 to 9 or image data from 0 to 9. The column sums to 45. We have 10 columns. And what we do is that we iterate over each element and we maintain this sum as the accumulation of the prediction of each digit. So sum should logically come out to be 450. Achar was able to generate the following invariant for this given program, which calls a convolutional neural network via the predict function. Finally, I would like to conclude by saying that we do proof fuzzing as compared to fuzz testing. That is, we don't fuzz the actual program, but rather the proof of the program, which are two completely different things. This fuzzing of this proof fuzzing allows us to work with checking invariants for opaque operations or programs that contain opaque operations. Along with that, it opens up the avenue for automatically synthesizing inductive invariants for real-world programs. And these real-world programs can contain multiple opaque components that cannot be handled by current theorem provers. Do note that the programs in our open benchmark suites could not be handled by existing tools. Thank you all for listening patiently to my talk. I am now open to questions. Achar is available on Docker Hub and also on Zenodo. The link for the same have been shown here. Thank you. Thanks a lot.